Next topic, this is the last topic of this chapter, moving coil in a galvanometer. We have to study, its working. Then we have to study its conversion into voltmeter and ammeter. In some books, the conversion part is even included in current electricity, that is the DC part. So our topic is moving coil, moving coil galvanometer. Galvanometer. Its working principle is the same what we studied yesterday. That its principle is that when a current carrying when a current carrying coil is placed in a uniform magnetic field. It experiences torque. It experiences a torque And what is that torque? We studied it. M cross B, or if we just write magnitude, then it is MB sine theta, and we write magnetic moment as number of const current, and the area NIA is the magnitude of magnetic moment, and B is the magnetic field, and sine theta, and see here, the magnitude of torque depends on the value of current. This is the key thing regarding the working of moving coil and galvanometer. Means the magnitude of torque depends on the value of electric current through the coil. Through the coil. This is the working principle. Now we'll discuss it a little bit about its construction. And then we'll study its sensitivity, its conversion. Now let's save this phone and let's look at its construction part. How does it work? See here, this is the cylindrical core. Cylindrical core, just like solenoid. In solenoid also we had a core of insulator, and we used to coil the wire over it. In the similar way, we have a cylindrical core here, and it is made of soft iron. So the first part is regarding construction. Construction, you have core, cylindrical core, cylindrical core, and it is made up of soft iron. Soft iron. Soft iron easily gets magnetized. Easily gets magnetized, and so it increases. It increases the magnetic field. Magnetic field intensity. Intensity. And then see, we need a strong, we need a strong, electric, magnetic field here, and that's why we have a circular, a circular magnet here, it produces radial magnetic field, and this is the turn of the coil, then we have to, this coil has a current, and here we have magnetic field. So what will happen, and then what will happen. It will experience a torque. It will experience a torque. We already studied that. If we want to, yes. If you see the actual figure, T is this is the 10 torsion head, torsion head, and we have a hair spring here. This one is hair spring, and for current, what we do, we don't have complete figure here. We need a source here, no? Source for electric current. So we will send current, we will send a current with the help of this source. So we have a current in the coil. You have a magnetic field, a radial magnetic field. Then see, the magnetic field is radial. The magnetic field is radial here, and your magnetic moment is perpendicular. So the angle between, so the angle between your magnetic field is present in this horizontal plane, and your magnetic moment is perpendicular to this. So the angle is 90 degree. Angle is 90 degree, and that's why the torque will be how much? N-I-A is the magnetic moment, B, and then the sine 90. Sine 90. So the torque experienced is N-I-A-B. Now, let's observe one thing. When it experiences a torque, it this will rotate, this will rotate, and if this rotate, then your spring, your this spring gets twisted, twisted. So a counterback torque, a counterback, a counter torque is produced because of the torsion of this hair spring, and that is in equilibrium condition. In equilibrium condition, or I will write a few lines, so you can 3 days later, how does it, it's mainly in a working part, we need, let's say, write in a little bit, and you have in a coil is made of uh, phosphor, bronze, then you have and this coil is suspended, it is suspended, from a movable torsion. This is in a torsion head. Torsion head with the help of we have wire here. No. This coil, this coil, this your wire is made of phosphor, phosphor and bronze, this is the wire is made of with the help of phosphor, bronze, wire, and later we'll see while studying in the conversion, we'll draw a simple diagram, and you will see that you also have a scale here in which you take the reading, and the scale is connected connected to this core. So when you're in a coil and it rotates, when you're in a coil it rotates, the pointer will also get deflected, and you have several readings here, and it will show different value. This pointer will point to different values depending on the value of current, because see our torque is proportional to current here. This is how it works. This is a scale here. So see the structure. You have a soft iron core. Then you have a radial magnet here for the magnetic field, and then this torsion head. Your coil is connected to the torsion head, and when you when the coil experiences a torque, it rotates, and when it rotates, then the spring also here gets twisted, so after some time, after getting twisted, when it gets twisted, a counter torque will develop. You cannot try this. You can take a rope and just twist it for some time, twist it and then leave it. You can see, you can observe a counter torque there, there, and its direction is opposite to the direction of the torque we applied. So let's move to the this working part. The working means when our coil experiences a torque, it's when just a little bit, write a few sentences and then we will do calculation. When an electric current, when an electric current is passed through the coil, is passed coil, through the coil, it experiences or it experiences a torque, given by NIAB, you have a sin 90 here because the magnetic momentum is uh, is perpendicular to the plane of the coil, and your field is radial here. Your field is radial here means it is your field is present in the plane of the coil in the horizontal plane. So magnetic moment and B, angle is 90 degree. So we have torque equal to NIAB here in this condition. As the angle is 90 degree. Now, when when it experiences a torque, means this iron core will as a result we can write the torque rotates the coil with the core, and see our spring is attached to the core. As a result, what will happen? As a result, the spring, the spring, yes, gets twisted, twisted, and a counter torque. As a result, a counter and a torque. A counter means it will have this the torque that will develop here because of twisting twisting of the spring will have direction opposite to the direction of this applied torque. As a result, a counter torque is produced in the spring. And the value of this torque, the value of this torque is proportional to the, how much it gets twisted, and what happens at a party. So as the spring gets twisted, the value of counter torque will go on increasing, and when it becomes, and when the counter torque becomes equal to the applied torque, then equilibrium condition will be developed. Means its value, its magnitude goes on, increasing, increasing, with time. And when our means at some point of time it will become equal to, at some point of time it will become equal to the applied torque. So equilibrium condition, you have this applied torque, IAB is equal to this key. This is the counter torque. Now, what is K here, and what is phi? We have to know that phi is the angle of deflection of coil, and K is a constant, is torsional constant of the spring, constant of the spring. See, when you're when your coil experiences in a torque, it will get in a deflected, it will rotate, means it will rotate, this means what, it gets in a deflected, so you will have an angle of deflection here, the more your coil gets in a deflected, the spring will get in a more twisted. So the value of torsional torque will increase. Means as the angle of deflection of the coil is increased, the spring gets more twisted, and it's and the value of the torsional or counter torque will increase. And K is the value of torsional constant for given a spring. Means its value will depend on the material of the spring. So we have this condition, and we can calculate the value of this K for a particular spring. It will be Ni AB by your phi. We can measure the value of this torsional constant of a given spring by just passing a current through the coil and measuring the value of angle of deflection of the coil, and you have values for these certain quantities: number of turns, current, area of coil, and magnetic field there. If you substitute the values of all these quantities, then we can find the value of torsional constant. This is one thing, and then let's move to the sensitivity part. Sensitivity. We have to study two sensitivity here. First is current sensitivity. Current sensitivity. What is the current sensitivity? See here, the value of torque depends on the value of current. The value of torque depends on the value of current. IAB. T depends on I. No, and the angle of deflection of the coil. Angle of deflection of the coil depends on the value of torque. So your phi depends on torque, and your torque depends on current. No, however, torque depends on angle of deflection. Angle of deflection of coil. Deflection of coil, and our torque is torque depends on an electric current in the coil. So what is the relation? Angle of this deflection is the angle of deflection of the coil, and it depends on what electric current in the coil. So this is how we see the relation between current sensitivity. So by current sensitivity, we understand now. We can just put a constant here. When we remove this proportionality sign, then we take a constant here. This SI, and this SI is the how much in a 5 by I, and this is called current sensitivity. This proportionality constant is called current sensitivity. So what is this angle of deflection of coil per unit current, for a unit current. Is this clear? Current and sensitivity, how angle of deflection will depend on the value of current. No, here we see that the angle of deflection of the coil is depending on the value of current in the coil. Is it directly proportional? And if we remove this sign proportionality, we take a constant here, and that constant is called current sensitivity. So current sensitivity is the angle of deflection of the coil per unit current, for a unit current in the coil. Now we have to calculate the value of this constant. Let's save this one. Is it clear? Current sensitivity. So let's calculate we have 5 by I, and just now we studied we just now studied torque. This is one thing. Now we have our torque, applied torque in equilibrium condition. We have applied torque is equal to counter torque of the spring, that is in a K phi. So the value of phi is NIA B by K. So this is our equation 2, and from 1 and 2, but we can write current sensitivity is your phi is NIAB by K, means Ki, and see here this I term will get cancelled, this I will get cancelled, and you will have current sensitivity as NBA by K. So from this relation you see current sensitivity depends on it depends on n number of turns of coil. If you larger number of turns, you will have higher current sensitivity. And what is the current sensitivity physically meaning? It is giving the relation of deflection of the coil on with the electric current. Because we know when we increase the value of current, the coil gets more deflected. So it depends on the value of means if you increase this value number of turns, then this will be high. It depends on your it depends on B, means in a magnetic field. If you increase the value of magnetic field here, in that condition also what happens, current sensitivity will increase. It depends on area of the coil, area of the coil, and it is depends on, but it is inversely proportional to torsional torsional and a constant of the torsional constant of the spring. Yeah, see this relation, and if this value is high, this will be low. No, so the relation is I will just remove here. Okay, we'll write it here. So if you have higher values of this torsional and a constant, and if this value is high, then your uh, current sensitivity will be low. Why? Because if you have higher values of the torsional constant, means you will get an equilibrium condition in a very fast. You will get in an equilibrium condition very fast because in a torsional constant is how much k times 5. So if the value of k is high, you get higher values of torsional and torque quickly, and soon an equilibrium condition will develop. Means your applied torque will soon become equal to this torsional torque, and then the coil can't get deflected anymore. So this is the relation, means in order to increase current sensitivity, we can increase number of turns, we can increase magnetic field, relation is directly proportional, and here better we write like this, I will put the arrow downward for better understanding that it is inversely proportional. So if you have low values of K, then we will have a greater current sensitivity of the spring. So let's save this one. Is it clear? Current sensitivity. We also get theoretical questions based on these factors. Current sensitivity, mostly current sensitivity, and rarely we get voltage sensitivity. Another topic here we have voltage sensitivity, voltage sensitivity. Now we have to here by voltage sensitivity we have to understand the relation between angle of deflection of the coil and the applied potential difference. So what will be the relation? See, we have V equal to V equal to IR. We have studied V equal to IR, and it is your PD. This is the PD potential difference across the coil. Means you are applied in a PD across the coil, and a potential difference across the coil is in a V, and see this voltage sensitivity, how it depends, how it depends on what is the relation between angle of deflection and this and applied potential difference. So if you have a higher value of potential difference, you will have a higher value of current, and when you have a higher value of current, means if you increase V, higher, if you have a higher PD across the coil, you will have a higher current, simple Ohm's law, And then if you have a higher value of current, then you will have higher value of torque. And if you have higher value of torque, and if the value of applied torque is large, then this coil gets more deflected, and it will get deflected through a larger angle. So this is the relation. This is how we see that on increasing, on increasing the applied voltage or PD across the coil, we can increase the angle of deflection of the angle of deflection of the coil. So see how is the relation. Our angle of deflection of the coil is directly proportional to the applied voltage. No, and here again, if we remove this sign proportionality constant, then we have to take a constant here, and this constant is called voltage sensitivity. This is called voltage sensitivity. It shows the dependence of an angle of deflection of the coil on the potential difference across the coil. So our voltage sensitivity is 5 by V. And how much is in a phi? We started now. And IAB equal to phi K. No? Then this set of phi will be how much in IA B by K. And IA B by K, and you have V already here. So let's save this one. And let's say start another session because it will stop and it will be difficult then.